This is A.1 Kinematics. Here's what we'll learn in this tutorial, and of course you have a record of all these in the Kinematics download underneath this tutorial. You could be ticking these off as you begin to understand them with me. Number 1, define displacement, velocity and acceleration. Number 2, explain the difference between distance and displacement. We'll start off by defining distance and defining displacement. Distance is defined as how much ground an object has covered during its motion. It is a scalar. If you don't know what a scalar is, head to the math skills tutorial that is attached to A1 Kinematics. Let's look at distance in more detail. We have an object here, and this object travels all this windy path from A all the way round to B. The amount of ground it covers during this journey is 250 metres. That's its distance. It doesn't matter the direction, that's how far it's travelled. However, its displacement is from the start point, as the crow flies, all the way to the end point. The displacement is defined as the change in the object's position. You can see it's changed position from A to B, and the value of that displacement is 128 metres, but because it's a vector, we also have to give the direction. East. If you don't know what a vector is, head to math skills. Let's define velocity now. It's defined as the rate of change of position, and it's given in metres per second squared. It is a vector. Acceleration is defined as the rate of change of velocity. It's got units of metres per second squared, and it's also a vector. You'll note here there's a little video here measuring the speed of a cyclist. It's got units of kilometres per hour, and it's changing throughout the journey. It's not a velocity, okay? This speedometer recording the cyclist journey is not velocity because it doesn't tell us what the direction is. It's recording this cyclist's speed, and it's just giving it in different units. Instead of metres per second, it's giving it in kilometres per hour. So we have to be flexible about how we recognise velocity, speed and acceleration, and we have to understand that whilst the preferred units are metres per second, you may be given it in other units as well. What I'd like you to do is take your blank revision note template, you can find that below this tutorial, and in the definition section, write the definition of displacement, velocity and acceleration in your revision note template, and then complete question 1 in the A1 knowledge questions. For learning objective 3, we're going to look at how to calculate instantaneous and average values of velocity, speed and acceleration. And we're going to concentrate mainly on speed for this. Let's just have a little bit of a further look at the difference between speed and velocity first, because in the previous section we looked at the definition of both of these terms, but actually it's very helpful to have an equation for both speed and velocity. So you can see that the equation for speed is speed equals distance over time. You know that, right? You'll notice that distance is a scalar, speed is a scalar. So distance equals speed over time. Always use the scalar quantity of distance to calculate speed. Velocity is a vector. So we're going to look for a vector quantity to calculate velocity. So the equation for velocity is displacement over time. Right, we live in the real world, okay? And you know that during any object's journey, whether it's a car, whatever it is, it will change speed a number of times. And if we take the car as an example, the speedometer in the car records the speed of the car's journey and will read different values. What that speedometer is really doing is it's recording the instantaneous speed of your car. Instantaneous speed is defined as the speed of an object at a particular instant in time. The average speed is different. What this graph is showing is an object travelling at 1 metre per second for 2 seconds. Then it travels at 3.5 metres per second for 1 second. Then it travels at 2 metres per second for 2 seconds, and it's constantly changing. How useful is that for us? Well, it'd be quite nice if we could just know the average speed of that car. And to find the average speed of the car, we'd use this equation. Average speed equals total distance covered divided by time taken. And I've prepared a question for you to complete for that in the knowledge questions. We'll look at that later. And the final term I want you to be aware of is something called constant speed. You're often going to see the term constant speed or steady speed in exam problems. For the purposes of kinematics, what that means is that the object is travelling at a steady or constant speed and its instantaneous speed has the same value throughout its journey. It means there's no acceleration or no deceleration. But if you see constant speed or steady speed in a forces problem, that means there's no resultant force acting on the object. Could you get your revision note template and write down the equation for average speed in your revision note template? You may also want to write down the definition for constant speed. And then I highly recommend you complete questions 2 to 5 in the A1 knowledge questions. Let's take a few learning objectives at once here. Number 4 is recognise situations where acceleration is uniform and non-uniform. Number 5 is understand that the equations of motion are only valid for uniformly accelerated motion. And number 6, solve problems using the equations of motion. Okay, the difference between uniform and non-uniform acceleration. Uniform acceleration are situations where the numerical value of acceleration does not change. And for IB physics, we are going to specify that to objects in free fall or projectile motion and objects in circular motion. When we're looking at these calculations, we always assume, unless otherwise specified, the air resistance is negligible. Non-uniform acceleration. That is situations where the numerical value of the acceleration does change throughout the journey. And in terms of IB physics, we'd be looking at 2 specific situations. They would be where a varied force is being applied to an accelerating pedal and where varied frictional forces are opposing motion. Should be able to explain these, but not calculate them. Now we know the difference between uniform and non-uniform acceleration. Let's look at one particular set of equations that rely on uniform acceleration. And this set of equations are known as the equations of motion. You will recognise these. Sometimes they're called the SUVAT equations because they have S, U, V, A and T inside them. They're the 5 quantities you find inside these equations of motion. 2 conditions of using these equations are the acceleration is constant and the motion is in a straight line. So you might notice a car accelerating along a road. If the acceleration is constant and the car is moving in a straight line, you can use the equations of motion. You might have a pebble dropping from the sky. If the acceleration is constant and its motion is in a straight line, you can use the equations of motion. I'd really love to talk you through the 4 rules of using these equations of motion to make sure that you use these equations and get full marks every time in IB physics exams. And I think the best way to do that is to go through an example. So we'll look at the example first. A ball is thrown upwards at a velocity of 25 meters per second from a cliff top and falls into the sea 6.1 seconds later. Calculate the height of the cliff above sea level, assuming air resistance to be negligible. Can we use the equations of motion for this? Well, we assume air resistance to be negligible, which means that the acceleration due to gravity will be constant at 9.8 or 9.81 meters per second. And we're throwing upwards and it's going to come down again. We can say that it's in a straight line. Yes, we can use the equations of motion. Always good to know. The first rule is to draw a sketch. We draw the sketch just to normalise the situation in our head. So I've drawn a very simple cliff, I've drawn the sea, and I've drawn a ball being thrown upwards and falling into the sea. The second rule, and this seems a bit abstract to students quite often, is to choose which direction is positive. And by that I mean, choose upwards or downwards. If you choose upwards as positive, then all the values that move up the way are given a positive value. So you can see this velocity of the ball at the start is moving upwards, so we're going to say plus 25. And any values that are down the way and are vectors, like acceleration, are given a negative value. Can you guess what this displacement vector would be given? Would it be given at positive or negative? Yeah, you're right. It's given negative because it's moved downwards from the start point, so it's got a negative value. Okay, so choose which direction is positive. I've chosen upwards as positive here, but you could quite easily choose downwards as positive, as long as you make sure all the quantities are labelled correctly. Rule number 3 is to write down the 5 quantities of equation motion, SUVAT, on the left-hand side of your paper, and start putting the number quantities to these labels. So the initial speed is plus 25, let's pop that here. The acceleration, it's going down the way, is minus 9.8. Let's put that here. The time taken for this whole thing is 6 seconds, 6.1 seconds. Let's put that here. And a question mark beside the displacement because we want to know the height of the cliff. So we know now that we need an equation that has S, U, A and T in it. So rule number 4 is to find which equation has S, U, A and T in it and then pop in the numbers and find the answer. So we've used S equals UT plus a half AT squared. We've popped all those numbers in, remembering the negatives where appropriate, and we come up with the answer of S equals minus 29.8 metres. Does that make sense? Yes, because it's 29.8 metres below, downwards of the cliff. So that makes complete and utter sense. I would like you to take your revision note template and pop in the 4 equations of motion into your revision note template. I'd also highlight in your revision note template the conditions of using the equations of motion. And I'd like you to try questions 6 to 9 in the A1 knowledge questions, using these 4 rules to help you lay out your work. Learning objective 7 is to define a projectile and resolve into vertical and horizontal components. Learning objective 8 is to solve projectile motion problems for horizontal, oblique and below horizontal projections. Let's define a projectile first off. A projectile is an object upon which the only force acting is gravity. So if you look above at the video here, we've got a person hitting a golf ball. And once that ball is in the air, and we assume no air resistance, the only force acting on that ball is gravity. There's only one force acting downwards, gravity. So that ball, again, assuming no air resistance, is defined as a projectile. If there were any other force acting upon that object, it would not be a projectile. When we look at projectile motion, and we've got this poor turtle who's been launched horizontally off a cliff, it's helpful for us to split out the velocities into 2 components. One is the horizontal component of velocity, and 2 is the vertical component of velocity. Let's look at horizontal first. When an object is in a projectile motion, its horizontal motion or its horizontal velocity always remains constant. It doesn't change in value. That means when we're looking at horizontal motion, we can use the equation speed equals distance over time. Because it's constant speed, it's very simple. When we consider the vertical motion of this poor turtle, we can see that the vertical velocity starts off quite small and it accelerates due to gravity. If we're looking at vertical motion only, this vertical motion is in a straight line and it accelerates constantly due to gravity. So when we're dealing with vertical motion, we use the equations of motion. When we deal with projectile motion, we want to completely separate out horizontal and vertical motion when we're doing calculations. With horizontal motion, we know that the velocity remains constant, there's no acceleration, and we use this equation here, speed equals distance over time. When we look at vertical motion, it uniformly accelerates. The acceleration is 9.81 meters per second, so we use the equations of motion. I mentioned different types of projectile motion. When an object's trajectory looks like this is called oblique projection. It's when an object is thrown upwards at an angle. To find the vertical component of velocity for an object in oblique projection, and to find the horizontal component of an object in oblique projection, we use these two little formulae. V equals V sine theta for vertical and V equals V cos theta for horizontal. If you want more of an explanation of why we use that, then head to the math skills tutorial of this topic. Examiners are actually quite good at giving feedback on the mistakes that a lot of students make, and one of the pieces of feedback from examiners in the past has been a common mistake was the incorrect calculation of resolving velocity for projectile motion. That means that this is important. When you have oblique projection, these two equations are important. You've got to learn how to use them. And of course, I will help you apply these when we look at the knowledge questions. Horizontal projection is when it's projected horizontally to begin with, and the trajectory looks like this. A key point in looking at projections like this is that the vertical velocity of the object at the start is 0. And we'll look at that when we start looking at problems later. There are rules in dealing with projectile motion. And the best way to deal with this is A, draw a diagram. I told you we've got to draw lots of diagrams. B, choose which direction is positive, just as we've done with the equations of motion earlier. And C, draw and complete this table. Because what this table does is it reminds you, okay, I've got to deal with vertical velocity different, it accelerates, and I've got to deal with horizontal velocity differently, it doesn't accelerate. So this table will become your friend whenever you're looking at projectile motion questions. In fact, why don't I just walk you through a worked example using this method right now. A typical example of an IB exam style question. A golf ball is hit with a club from ground in a large gym hall. The ceiling of the gym hall is 6.5 metres. The initial velocity of the ball is V equals 15 metres per second at 50 degrees above the horizontal. Assume the air resistance is negligible. Determine if the ball will hit the ceiling. Okay, so rule number 1 is to draw a diagram. Some exam questions may already have a diagram you can annotate. In some exam questions, you would have to draw one from scratch. In this case, we have a diagram we can annotate, so let's do so just now. The first piece of information tells us that the ceiling of the gym hall, let's draw a ceiling here, is 6.5 metres. So let's pop that in. The initial velocity of the ball is 15 metres per second and at 50 degrees. Is there anything else you want to add there? Well, let's go to rule number 2. And rule number 2 was to label one direction as positive, or choose one direction that you would link as positive. And I usually go upwards, so I'm going to write an arrow on here, and I'm going to say upwards is positive. And I'll show you how that makes a difference in a second. The third rule was to draw the projectile motion table. And let me show you exactly what that is just now. Very simple table with 2 columns. The first column is the vertical column, and the second column is the horizontal column. Now, in this tutorial, I've highlighted how important it is to manipulate the vertical velocity completely in a separate entity from the horizontal velocity, because the vertical velocity undergoes acceleration, but the horizontal velocity remains constant. And with those two different types of motion, we use different types of equation. With the vertical velocity, which is undergoing constant acceleration, we would use the equations of motion. And the 5 different variables in the equations of motion are displacement, initial velocity, final velocity, acceleration, and time. So we pop those 5 variables in the vertical column. The horizontal velocity undergoes constant velocity. So we're really only looking at the equation speed equals distance over time. And that is the 3 different variables we're looking at for horizontal velocity. So we've done rule number 1. We've drawn a diagram. Rule number 2 is we've chosen a direction for positive. And rule number 3 is to draw and complete the projectile motion table. So let's complete that table now. We want to know what the maximum height of the ball is. So maximum height, we're looking at vertical motion. So we want to know what S is, the maximum height. The initial velocity of the ball is U, and we can see that this ball does have initial velocity. It's being hit by a golf club, and it will initially have velocity. But the initial vertical velocity of the ball will not be 15 meters per second. It will be the vertical component of that. And we have to use our understanding of trigonometry or SOHCAHTOA to work out what that vertical velocity would be. And in this case, it is 15 sine 50. The final velocity of the ball, when it reaches maximum height, will be 0 meters per second. And the acceleration will be minus 9.81 meters per second squared. So why have I put a minus there and a plus there? Well, if we go back to the diagram, you can see that the initial velocity of the ball is upwards, and we've chosen upwards as positive. So U has a positive value. Acceleration drags objects downwards. So acceleration will have a negative value, as shown here. So we've drawn our diagram, we've chosen direction as positive, we've completed the table. There's a couple of other things. Well, there's one other thing we could put on here. The horizontal speed of the ball would be 15 cos 50, but I don't think we're going to need that in this question. So now we have to decide, to find out what S is, which of the equations of motion should we choose? So we need to choose an equation of motion that doesn't include t, because we don't have that information. And we need to choose an equation of motion that allows us to find S. So the equation of motion that springs to mind would be v squared equals u squared plus 2as. We put the data in. So v squared is 0 equals 15 sine 50 squared plus 2 times minus 9.81 times s. We can take this quantity over to the other side. So we've got minus 15 sine 50 all squared equals minus 2 times 9.81 times s. Minuses cancel. And once you play about with your calculator, you will come out with 13203 equals 19.62s. So S equals 6.73 meters. You will notice that this answer is given to 3 significant figures, and all the data has been given to 2 significant figures. We have 15 meters per second, 50 degrees. So we want to shorten this down to 2 significant figures. So S equals 6.7 meters. The original question said, determine if the ball will hit the ceiling, and the ceiling was 6.5 meters high. So yes, the ball will hit the ceiling as its maximum height will be 6.7 meters high. What I'd like you to do now is write down the definition of a projectile in your revision note template. I'd like you to record the projectile motion table and the projectile motion diagrams of oblique and horizontal projections in your revision notes. Then head to questions 6 to 9 in the A1 knowledge questions, and let's get them done. So far we've been discussing the ideal conditions of projectile motion, neglecting all the effects of air resistance. However, in the real world, air resistance plays a significant role in the motion of a projectile. I'd like to start by looking at the effect of air resistance on the trajectory path. So in an ideal situation without air resistance, the trajectory of a projectile is a perfect parabola, as shown by this blue line here. However, with air resistance, the path deviates from this perfect parabola shape, and what you can see is this red line here. It doesn't travel as high, and the horizontal distance covered is also reduced. So what that means is The trajectory of a projectile with air resistance is less spread out and it drops more steeply than the ideal parabolic path. Now let's look at the effect of air resistance on the time of flight. Air resistance tends to shorten the time of flight that a projectile takes to reach maximum height. That's because air resistance decelerates the projectile's upward motion. Air resistance decreases the upward velocity of the projectile more rapidly than gravity alone would. Similarly, the horizontal velocity is also reduced due to the opposing force of air resistance, meaning the projectile doesn't travel as far horizontally. If we think about the effect of air resistance on acceleration, air resistance decreases the upward velocity of the projectile more rapidly than gravity alone would, which means that increases the downward acceleration of the projectile. And for downward velocity, the force of air resistance opposes that of weight, which means the unbalanced force, which is causing the downward acceleration, is less. And this decreases the downward acceleration of the projectile. And if we really just put that into 2 bullet points, on the way up, vertical acceleration is increased, and on the way down, vertical acceleration is decreased. Terminal velocity is when the upward force of air resistance balances the downward force of weight. These balanced forces cause constant velocity or constant speed. It's a good idea to learn this definition and put it in your notes. Here we go. Terminal speed or terminal velocity is the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. We've got to the final section of kinematics, and what I'd like you to do is take your revision note template and go to the common graphs section, and I would like you to draw down the graphs of the trajectory path with air resistance, the time of flight with air resistance, the velocity and acceleration with air resistance, and then go to the definition section and write down the definition of terminal velocity. And finally, to complete this whole topic, can you go and complete question 10 in the knowledge questions? We've raced through kinematics, and the next stage for you, now you understand all the concepts, is to work out how to apply these concepts in exam style questions.